morning to all of you. As I've told you in the last class that the subject which we are covering is a very important subject in the sense that the entire electronics today, and not only electronics, almost all other disciplines are based on the gradual development of VLSI circuits and systems, which have simplified the entire electronic systems to a great extent. Today, I wish to cover, or rather I wish to give you a brief review of the basic ICs, that what way an integrated circuit is different from a discrete component electronic circuit, okay? In what way an electronic circuit, a VLSI, is different from a discrete component electronic circuit. As you know that the two basic elements, basic components, one is called bipolar junction transistor, the other is MOSFET. One is bipolar junction transistor, the other is metal oxide semiconductor field effect transistor. These are the two basic active components which comprise any VLSI circuit today. Of course, BJT is still in the domain of up to LSI, but there is a great potential, particularly as we shall discuss afterward, with the advent of integrated injection logic, I2L. Bipolar transistors have also gone into the field of VLSI. BJT basically is a structure something like this. As you see that this basic structure of bipolar junction transistor is made of a p-type silicon substrate. This is a p-type silicon substrate which is sufficiently thick, maybe up to 500 micron thickness. The thickness of this is up to 500 micron. And this p-type substrate, on the top of which there is an epitaxial film, which is N-type, and has got a very small thickness, maybe of the order of 5 micron. The thickness of this epitaxial film, which is grown on this p-type silicon substrate, is around 5 micron. It is not necessary that it should be 5 micron only, there may be a range. While the old transistor had thicknesses, epitaxial film thicknesses around 20 micron, the most advanced bipolar transistor of today has a thickness of even 1 to 2 micron epitaxial film. Please remember this. Then the basic bipolar junction transistor, as you see here, is within this region, which is an island of N-type epitaxial film from here to here. It is an island of N-type epitaxial film surrounded by all P plus regions. You see that in the bottom side there is P-type substrate, whereas laterally, sideways, there are P plus isolation regions. These regions are called isolation regions. Isolation. So our transistor, so-called NPN transistor, is located inside a N-type island, which is nothing but a small portion of epitaxial film surrounded both downward and sidewise by P-type material, so that this island is nothing but its surrounding structure is a PN junction. And if you look at this sorry, I think this is not P plus. This is again by mistake I have written P plus. This is N. And this is also N. What I have done here, I have shown only a portion of a bipolar IC where only a single vertical NPN transistor has been indicated. This is called a vertical NPN transistor. Vertical. And on either side of this basic block N, into which the transistor has been realized, there are also N-type islands. In the right hand side, one N-type island which I have just shown only partially. On the left hand side, there is another N-type island which I have also shown partially. Similarly, out of the figure and down from the figure, that means sidewise on the other direction, perpendicular to the plane of the figure, there are also N-type islands. So you please see that the entire structure now consists of a P-type substrate on which there is an N-type film initially. Then by some process, I have divided that N-type film, N-type epitaxial film, into a number of islands or blocks or tubs. They are also called tubs or wells. Various terminologies are being used nowadays. Some people call it tubs, some people call it wells. Or we can also like to say island, because these are really islands floating in a P-type sea. And in each island, we develop a component. For example, an op-amp consisting of, say, 50 transistors, around 60 resistors, what we can do is we just divide the N-type layer on the P-type substrate into around 100 or 110 blocks or islands or wells or tubs, and in the various wells, in the various tubs, you develop your different components. In this case, they are transistors, resistors, and maybe a few diodes, or maybe a few capacitors also. And these are isolated electrically, and the kind of isolation is normally called junction isolation. Junction isolation. The different transistors or different resistors or different components in a chip, they are electrically isolated from each other through reverse biased PN junctions. And you know the property of a PN junction. What is the property of a PN junction? Under forward bias, it is highly conducting. On the other hand, when you reverse bias it, it is very poor conducting, and it offers a very small capacitance also. You remember the capacitance versus voltage characteristic of a reverse PN junction diode. What is the nature? As we increase the reverse bias, the capacitance gradually decreases. And therefore, what we normally do while operating such an IC, bipolar IC, we keep the substrate at a reverse bias with respect to all the islands. If you keep the substrate, that is P at a negative potential with all N-type blocks, you know the N-type blocks here. So for example, this one, this N-type block is connected to, is nothing but the collector of the transistor, and this is an NPN transistor, so the collector gets that maximum positive voltage with respect to emitter. So automatically, and sometimes either you keep P-type substrate grounded, or sometimes you can also keep it to a large negative potential depending on the application, so that all such islands situated on the P-type substrate are reverse biased. And because the material is silicon and not germanium, what is the advantage of silicon over germanium? Silicon is a wider bandgap semiconductor, so its leakage current is very less. Its temperature sensitivity is also quite less compared to germanium. That is why, and the technologically silicon is superior, because this oxide which I have shown here, the red region is nothing but a silicon dioxide, which is grown by thermal technique, simply by oxidation of silicon using oxygen or wet oxygen, oxygen plus water vapor. And this is a very simple process. And this passivation or oxidation can be used as a mask for selective doping or selective junction formations, which are so important for the realization of a transistor or a diode. So you have to form, you see that you are doping first only up to this region, or this region, this selectively. And that was permitted, that was possible because we have grown a very nice quality oxide. Then by using a technique called photolithography, we etch windows in appropriate locations, then doped impurities by either the process of diffusion, impurity diffusion, or by ion implantation. As you know that either the diffusion or ion implantation, these are the two very important processes used in IC technology for introduction of impurity atoms in a semiconductor for the formation of PN junction. And that is a very important thing. You have to form several PN junctions to produce your end device. Say for example here, a bipolar junction transistor. So this is the thing, a typical bipolar junction transistor and a part of IC showing a BJT is like this, where it has been clearly shown that the bipolar transistor has been developed on an N-type island, on a typical N-type island. At the same time, you please note that there are hundreds of such N-type islands on the surface. They are isolated from each other by P plus diffusion. These P plus diffusions are called isolation diffusion. Looking carefully now, if I examine the structure very carefully, you see that I have at the bottom between the N-type epitaxial island and the P substrate a strongly doped N plus region, and that is what is known as buried layer. Buried layer, B-U-R-I-E-D, buried layer or buried collector. This one is also called buried collector. Buried all right, okay, and then you have an N plus diffusion starting from the collector contact. This one is called deep collector or deep collector diffuse region. Why it is necessary? Simply to reduce the resistance of the collector, the series resistance of the collector. If I do not have an N plus diffusion from the surface down to the buried layer, so that the buried layer, N plus buried layer is connected by that diffusion, the series resistance of the collector will be appreciable, which is not good. As you know, when the transistor handles a lot of current, if the series resistance of the collector is large, then two problems are. The one is as a power transistor or the driver transistor, you know there will be dissipation in the transistor, which is not good. And secondly, as a switch, there will be appreciable voltage across the transistor when the transistor is on or in saturation, which we don't need. We need that when the switch is on, the voltage across the transistor should be as low as possible, almost 0 volt, around nearly 50 to 200 millivolt. That's a typical requirement. But because of the resistance in series with the collector, normally called RC saturation, I think you know that, the resistance which is offered by the collector in saturation region is called RCE saturation. And that should be kept as minimum as possible. That is why we use a buried layer in the between the collector and the substrate, a heavily doped N plus region, and a deep diffused collector, so that the series resistance of the collector is as low as possible. That means our RC saturation is small. This is very important. Then you note that we have a P-type layer. This is P. We have a P-type layer in that N, which forms a base. This is your base. This is base layer. And within the base, again, we have, I think it is not readable very clearly, I am showing it separately. This is N plus. This region is N plus. Okay? This N plus is the emitter. So within the base now, first within the collector we have a P-type diffuse layer called base, and then within the base we have an N plus diffuse layer or implanted layer called emitter. And ultimately we have to get contact. So what we do, we deposit a suitable metal, normally aluminum silicon. This metal is usually aluminum silicon alloy. In today's technology, it is aluminum plus around 2% silicon alloy. Today's VLSI technology prefers to use this particular metal. It has got a lot of advantages. It has got a very low conductivity and excellent adhesion with the substrate. And also something else, some more modern things which I have not incorporated. For example, people would put a titanium layer in the interface. Titanium silicidation, all these things are there, but let us not consider here. So thing is that this one, this aluminum silicon layer, or mainly aluminum, is patterned photolithographically to form a final metallization. Here I have shown only the emitter base collector delineation. I have shown that how the metal has been etched photolithographically, so that we get the three things: emitter, base, and collector electrodes. Requirement is that the contact resistance should be very low. the metallization should be such that the contact resistance should be very low, and these contacts are ohmic contacts. These contacts should not be rectifying in nature, they should be ohmic. Means that its IV characteristic should be straight line passing through the origin and will show a very, very low resistance. That means the slope of that characteristic should be very, very steep. The IV characteristics of a good ohmic contact should be like this, almost vertical. This is I and this is V. I have shown a bad ohmic contact. Ideally speaking, a very good ohmic contact should be practically a vertical characteristic, which show a very low contact resistance, as well as on both sides the resistance is the same. So it is an ohmic contact. So these contacts have to be properly satisfied, and that's how we get the emitter, base and collector of a transistor. You have noted that on the emitter we have got this is N plus region, so we have a contact. On the P base I have a contact, and on the N plus collector there is a contact. Whole N-type layer is collector, but for taking contact we have taken it from N plus, and the current, as you know, that is a vertical structure, current will be flowing like this, mostly will be flowing like this, and ultimately it is laterally collected like this. Okay. Another very interesting thing to note is that whereas these dimensions, the junction depth, the epi layer thickness, etc., they are of the order of microns. This emitter junction depth may be around 1 micron. The base collector junction depth may be around, say, 1.8 micron or 1.6 micron, whereas the entire epi layer, as indicated here, is around 5 micron. And on the other hand, what are the dimensions of the structure horizontally? These are all vertical dimensions, is it not? Layered dimensions. But what are the dimensions horizontally? They are normally of the order of tens of micron to hundreds of microns. So these dimensions, they are very large. The horizontal dimension, if I say that this is my y-axis, this is y, and this is x, along y-axis, the dimensions are of the order of tens to hundreds of microns, whereas along y-axis, along x-axis, along y-axis, the dimensions are of the order of tens to hundreds of microns. On the other hand, along x-axis, normal to surface, the dimensions of the order of microns or even sub-microns today in very dense circuit. So the figure, whatever I have drawn, this is not the real life figure. So I cannot draw that kind of figure. In that case, I cannot show. If I want to maintain the scale, it is difficult to draw such structure. So please remember, therefore, the currents in a vertical NPN transistor, why they are called vertical? Because the currents are mostly vertical in the active region of the transistor from here to here. The active region of the transistor, currents are mostly flowing vertically. Ultimately, through the buried collector, it flows laterally down to the contact, up to the contact here. And similarly, from here through the lateral base, it ultimately, the base current flows like this. Collector current flows like this, base current flows like this. So currents, please remember, they are mostly vertical, and therefore such transistors are called vertical NPN transistors. In an IC, most of the transistors, bipolar IC, most of the transistors are bipolar vertical BJTs. Whereas on the other hand, there are some lateral transistors are also used. They look like this. They are called lateral transistor. I am showing here. This is vertical, lateral transistor, lateral BJT. It is something like this. Very simple. Okay. This is a typical lateral transistor. You see that here, this may be emitter and this may be collector, or vice versa, and the entire N region is base, and that should be a contact. I have just not, I missed that. Actually, I should have shown a contact here. Okay, like this. N plus. This is your base. I have not shown. I just forgot to show that in this diagram. Actually, the N plus buried layer is extended up to this, and there is a contact. You see that what has been done here, just this is an N-type region, that epi layer is one of the islands where a transistor or any component can be blocked, can be developed. And you see that there are two p-type diffusions or implanted regions. One of them, there is a detailed structure, let us not go into that, how exactly look like. But you see that if one is this junction is forward biased, this PN junction is forward biased, then it will inject holes into this base. In this case, this N-type region is base. And if this is reverse biased, those holes will be collected. So you'll get a transistor action where this one is emitter, this one is collector, and this one is base, means that so-called collector contact. In this region, which one is collector is nothing but base in the secondary bias region. Such a transistor is called a lateral PNP transistor. What is your guess about the performance of the two transistors? Yes? Can anyone of you tell? How the two transistors, the one is a vertical BJT shown here, the other is a lateral PNP transistor shown here, how their performance will differ? Any one of you? Which one will be superior in performance? Vertical. The gain will be much higher. In the lateral transistor, you see that normally it is rather difficult to achieve a gain of 10, beta of 10, because here this is the so-called base region, and this base region is defined by photolithography, where I have some limitations. Whereas here the entire structure is determined by the junction depths, and I can control that very precisely. Whereas a physical base width of around 0.6 to 0.8 micron is a rather simple thing in a vertical transistor. Achieving a 3 micron base length, base width, is rather difficult in PNP, lateral PNP transistors. Secondly, there are certain other problems, and it can be shown that lateral PNP transistor cannot be a substitute for the vertical NPN transistors. What we do normally, most in the circuit, most transistors are vertical NPN transistors, whereas in certain cases, you know, that's a complementary symmetric pair. Suppose I want to use an active load, a PNP transistor as a load. In that case, we use such lateral PNP transistors. So you'll find in a practical BJT, by practical bipolar IC, a good number of lateral PNP transistors like this. Okay, and majority of the transistors are, of course, vertical BJTs. Please remember this. Now, in order to optimize, which I perhaps was discussed in the device class, in order to optimize the performance of these transistors, we have to play with the following. One is, what are the things we have to play with? One is geometry, the mask's geometry. Different dimensions, what will be the emitter length, base length, width, etc., etc. It's called geometry of the masks. The first thing is geometry of the mask. Second thing? Power delay. Yes? Power delay power comes afterward. You know that to optimize the transistor means I have to improve all its properties. Ultimately, the FT, the cutoff frequency, is a very important parameter. Beta is an important parameter. You know that breakdown voltages are important parameters. Junction capacitances are important parameters. And Like that, there are so many very important parameters associated with the transistor. I want to optimize them. So what I should do in the fabrication stage? Can any one of you tell me? One is, as you rightly said, geometry. What I should do? I should increase the geometrical the sizes of the masks or side device dimensions, or decrease it. Decrease it. But please remember, by that I am losing the power. Okay, let me, because in most applications high power is not needed. Only in the buffer stages, outputs, we need power. But in most cases, we need simple voltage amplifications or some switching in digital. Only the output side, therefore there are separate power stages called buffer amplifiers. So power is not a, so far as VLSI is concerned, we want to reduce power. Ultimately, the battery life should be extended. That is a very important thing. Yes, therefore, by reducing the size, in what way, can you tell me how, suppose if I just scale it down by a ratio, the length or width is scaled down by a ratio alpha, what will be the improvement in power? By what ratio power will improve or decrease? Power alpha square. So there are certain scaling laws associated with this parameter alpha, which is called the scale down ratio. Okay. And then what else? One is geometry control. What are the other thing you have to do? Doping profile. The doping, that is a very important thing. How the doping atoms are distributed, what are the density, what are the peak concentration, what are the junction depth, what they look like, actual profile, how they look like, etc. And these are today, of course, can be done very precisely with the help of simulators, which are known as process simulators. I think you have heard of a name of a simulator which is called Supreme. Some of you must be knowing that. SUPREM. This is originally developed by Stanford University. So, and they gave the name Supreme Stanford University Process Evaluation Models. Stanford University Process Evaluation Models. And there is a series of versions available, started with 1, 2, 3, and now Supreme 4 available. Initially the models, the distribution was one-dimensional, and nowadays they are getting two-dimensional distributions also for multi-layer structure. Very complicated things have come up. So you have got something so that you can control your temperature, time, implantation dose, energy, etc., and get a profile. And using that profile, then I have to now analyze the device, the bipolar transistor. I have got at the input two things. One is the doping profile, and second is the structure plus the dimensions of the mask. Now I should have something to calculate the device parameters, and what I should use. Either you can go back to your days of this second year or third year, that device course, and take some formulae and try to calculate. You will find that you are very much limited in that approach. Very much limited in that approach, because you want high precision now. And again, you have to take help of a commercial simulator. For example, a simulator called Bipole is available. Bipole is available. Bipole, it was developed by University of Waterloo, Professor Ralston, Professor Ralston of University of Southampton, University of Waterloo, Canada. He developed, and this is very popular now, Bipole 1, 2, 3 versions are available. And using that, where supreme output is as the input of Bipole, you can now calculate the transistor parameters very efficiently with a lot of accuracy. People have done it. And for your information, in IIT Kharagpur also, we are trying to develop a bipolar device simulator. We have named it BIAS for certain name. I will not give you why it is called BIAS. The device simulator has been named BIAS. It has been independently developed. It is also the efficiency for using certain, but we are trying our best to make it as good as possible. And it is a total indigenous development. So such a simulator can be used for the extraction of the device simulates device parameters. And ultimately, what is our ultimate aim for bipolar IC? Transistor is only one intermediate one. I want to have circuit. So what I will do now? Suppose if any one of you, I ask, say, you to design a simple amplifier, maybe a differential amplifier with certain specifications. What are the specifications of one differential amplifier? One is a differential gain, the other is CMRR, and maybe some input and output impedance. So I specify those parameters to you and ask you to design such an amplifier. So what will be your approach?
We go more with simulation first of all.
Simulation means firstly you have to have your textbook knowledge. You know the configuration of such an amplifier, DFAM. You know that a good DFAM needs a constant current source in the emitter rather than a resistive load. All this information, so you can always start with something which you have acquired from your textbook knowledge. Okay, now either you take help of your elementary circuit knowledge based on, say, a book like Millman-Halkias, for example, and write down equations of either maze equations or nodal, for starting from equivalent circuits. You write down those equations and then analyze it. You can do that and you will not be getting very bad figures. Only thing, sometimes the equations are difficult and therefore you just you just have a numerical approach if some 5-6 equations have to be solved simultaneously, okay, rather than you take the matrix approach and take the help of the computer to solve the various currents and voltages, and ultimately you get those figures. This is one approach. But yeah, okay, this kind of approach is all right for a small circuit. But when you are considering a circuit of 50-100 transistors, even that small circuit, this is a very small one today. A circuit IC consisting of 50-100 transistors is a very small one. But can you do it by that approach which I have just now told you? No, it is not possible because it becomes very, very complicated in that case. And again, either you develop yourself or you take help of others. And fortunately, we have got I think you are using, many of you perhaps have used that, a program called SPICE, SPICE, originally developed by University of Berkeley SPICE. And of course, some people say, I think it was originally developed by a British group kind of thing. But anyway, it was, people normally say that it is developed by University of Berkeley at USA. And the SPICE again, various versions, a very advanced SPICE is available today. And only thing is, you can now simulate the entire performance of the circuit consisting of the different devices and components just by defining them in a proper way. Resistance, yes, I have used this resistance. I have to define the resistance values associated with the peripherals. You know that a resistance in an IC, we shall be discussing that afterward, is not a simple resistance. It has got associated capacitances, it has associated even inductance, and also it has associated parasitic transistors. A resistance does not mean a simple resistance. You have to take all these things into account, and this entire information can be fed to a program like SPICE called Circuit Simulator. SPIC is a very, pieces is another thing is called pieces. There is different SPICE and PSPICE is there. The PSPICE means that PC compatible. For the PC you DOS under DOS. PSPICE has come, and this SPICE can ultimately be used for the simulating the behavior of the whole circuit, where all the components, starting from transistors down to diodes and resistors, they are simulated nicely, taking into account all parasites. And you can ultimately get both the DC behavior and AC behavior of the circuit. That means if you want to know first the DC conditions, what are the various voltage levels, etc., that you can determine. Alternatively, you are finally interested in the AC behavior because that was the specification given to you. This should be the, so what you will be doing? So how to design now? Suppose your ultimate specification was so many, say 70 dB CMRR, maybe 60 dB differential gain, so many kilo ohms input impedance, so many ohms output impedance kind of design was there, isn't it? So this is the way I have stored. Is it a design technique? The way I have discussed, you start with supreme, have a process, have a doping profile, then tentatively design the transistor geometry, feed these two figures into bipole, get the device parameters, and take them as input to SPICE, run SPICE for the whole circuit, find out the ultimate things, and you may get something which is totally different from your original specifications. So what you have to do now? You have to now, yeah, that's the thing, that's iterations or optimization. You have to go on doing with parameters. Either sometimes we start with supreme, that means that even starting from the process. But if we find that no, I cannot do anything else for the process, I will start with the other things. So there are many opportunities to optimize the whole thing till I achieve my specifications. It is a very, very difficult job. That is why initial design cost of a full custom IC, even in the ordinary op-amp, the initial design cost is very, very high. Such ICs are called full custom IC. Means you start from the device level and ultimately land up with the full IC chip. And here so many iterations are involved and so many expensive computation time is involved to get the ultimate thing for a good circuit, that it is going to be a most very complicated affairs, and full custom design